What's up, guys? Welcome to class 114. We're still going to talk about electric potential, a related topic to it. Don't forget our equation for electric potential. Let's see what we got there. We got V, that means electric potential or voltage, equals W, work, with work or energy, over Q for charge, all right? So that's our equation we're using today. So just to practice from last class, try this one out on your own first. A 1-volt battery, so there's my voltage, or electric potential. Again, those terms are interchangeable for our purposes here. All right, how much kinetic energy? So we're looking for work, which is the same as energy. Does this battery provide to a single electron? So there's Q, negative 1.6 times 10 to the negative 19 coulombs. I'm going to add one caveat to that. I'm going to say, what is the magnitude of the energy given to it? All right, so V equals W over Q. V, 1. I'm going to leave the units out for now. 1.6 times 10 to the negative 19. All right, cross multiply, you get W, or the work, equals 1.6 times 10 to the negative 19 joules. All right. So we frequently deal with electrons and how much energy they gain or lose, or how much energy an atom gains or loses, depending on how the electrons move from one orbital to another. We'll get into that more in the last unit. Physicists don't like to use these small numbers all the time, right? They use these really small numbers all the time. No one wants to deal with 10 to the negative 19, 10 to the negative 18 joules. All right, so we make up our own unit. And when we deal with the atomic scale, frequently we do things in terms of electron volts, all right? Electron volt. Abbreviated lowercase e, capital V. Okay, what is an electron volt exactly? I'm going to write this down here. 1 electron volt equals energy gained by 1 electron, or 1 elementary charge, in 1 volt. Okay. Wait, didn't we just do that problem? Yeah, we actually kind of did. So let's rework the previous question. We're going to do it a little bit differently, though, all right? So let me just scroll. I'm having trouble scrolling for a second. Oh, it's giving me trouble scrolling. Oh, there we go. But can I scroll? That's strange. I wonder if I do this, if that'll work. You know what? I'm just going to close this app and reopen it. Give me a sec. All right, so let's rework this previous question a little bit differently. So voltage is still 1 volt. We're still looking for the energy, or work. But instead of Q writing 1.6 times 10 to the negative 19 coulombs, by the way, for this one, negative, positive, doesn't really matter. We usually look for magnitude, but I guess you could leave the negative in there. It's really not a big deal. But anyway, for Q, what we're going to write is 1E. What does 1E mean? That means 1 elementary charge. Did we learn that before? Yes, we did. Oh, bless me. All right, so right here we see 1 elementary charge, abbreviated with an lowercase e, is 1.6 times 10 to the negative 19 coulombs, all right? So what we have here is, let's see, V, let's fix that. V equals W over Q. 1 volt equals work over 1 electron. Cross multiply, we get that the work equals 1 E times V. Oh, there we get 1 electron volt. Wait, so you're telling me that 1 electron volt equals 1.6 times 10 to the negative 19 joules? Yes, I am. Highlight that. That's a really important point. You have to memorize that. Of course you do. It's not like we have a reference table or anything. No, so it is on your reference table. If you look, let's see, right here, it says 1 electron volt, EV. 1.6 times 10 to the negative 19 joules. So you can convert to and from all the time. So some people always do their work in terms of joules and then convert to electron volts. Some people do it the other way. All right. So let's try this question 2 different ways. So a proton is moved. Actually, you should try it first, then I'll do it. So pause the video. All right. Hopefully you gave this a shot. Let's see how you did. So a proton, there's Q. 1.6 times 10 to the negative 19 coulombs. Is moved through a potential difference of 10 volts, so that's V, in an electric field. How much work was required to move this proton? Solve in both electron volts and joules. So you can do the work in joules first, and then convert to electron volts, or you can just do it separately both ways. We'll just do it separately both ways. Let's just box this off for a second. First, we'll do electron volts. So in terms of electron volts, okay. In terms of electron volts, Q would also be 1e, right? 1 elementary charge. So V equals W over Q. Keep things small, no units. 10 equals, let's see, so I'll call it 1e. Okay, well, 10 volts, so you can kind of see it. Cross multiply, you get the work done here is, looks like 10 electron volts. That's one way to do this. Other way to do this question. Let's do it in terms of coulombs and then joules. V equals W over Q. Let's see, 10 equals, I was going to make this line clearer. All right, 10 equals, let's see, W's are unknown. Q is 1.6 times 10 to the negative 19 coulombs. Cross multiply, you get that W equals 1.6 times 10 to the negative 18 coulombs, or excuse me, joules, rather. So, two different ways to do this. Notice how we see 1 electron volt is 1.6 times 10 to the negative 19. So 10 electron volts is 1.6 times 10 to the negative 18. All right, 10 times as big. Kind of makes sense. All right. We're dealing with new units and stuff, so I know it can be confusing. It just comes with practice, though. So we can also convert from joules to electron volts and vice versa. See the reference table. We already mentioned that. But on your reference table, if you didn't write it down already, 1 electron volt equals 1.6 times 10 to the negative 19 joules. So we're going to use that conversion factor. So the first one here says 13.6 electron volts is required to ionize hydrogen from its ground state. How many joules is this? We'll get into what that means later on as far as like what that question actually means. But let's start with 13.6 electron volts. So we want joules, right? It's what you want over what you have. So we're going to multiply by 1.6 times 10 to the negative 19 joules over 1 electron volt. Electron volts cancel. I'm going to make that clearer. And let's see what we get here. 13.6 times 1.6 times 10 to the negative 19. We get 2.176 times 10 to the negative 18 joules. How many electron volts? Oh, so now we're doing a different question. Let's see. A 4.5 coulomb charge gains 5.4 times 10 to the negative 12 joules of electric potential energy. How many electron volts is this? This is excess information. You don't need that. 5.4 times 10 to the negative 12 joules. All right, so again, it's what you want of what you have. So we want electron volts. So 1 electron volt over 1.6 times 10 to the negative 19 joules. Joules cancel. And basically what ends up happening is you kind of get something like 5.4 times 10 to the negative 12 divided by 1.6 times 10 to the negative 19. And you get 3.375 times 10 to the 7th joules. All right. So there's a little bit of conversion, a little bit of work with electron volts. Students always ask, how do I know whether or not they want the answer in joules or electron volts? If it's a free response question, you can do it either way. I tend to go towards joules. If it's multiple choice question, electron volts will be in the answer choices. So it kind of gives it away there. Oh, look at that, some old Regents questions. So these questions are what you are going to submit in your Google form for your like exit ticket, if you will. So make sure you do good work for them. You should make sure you do the work on, you could do a separate piece of paper if you didn't print it out. Make sure you show all your work and circle your final answers. So I'm actually just going to circle and highlight the answers here, and then your responsibility is obviously to show the work. So just give me 1 second so I can make sure I circle the answers correctly here. I think this one's going to be choice 4. I'm trying to do these in my head. Hopefully I didn't make a mistake here. That'd be embarrassing. And then let's see, A to particle, 3 charges. I think this one's going to be like, yeah, right there. Okay, so just your task obviously then is to show the work for how I got those answers. I was able to do the math in my head, so it's really not that hard. If you're stuck on 7 and 8, Why don't you look back to number 5, when we did this part here, or number 4, okay? But if you're confused, shoot me an email, stop and Dexter out, do them right. The last little bit here, this is kind of an extension topic, but one that does frequently show up. So we've seen question 14 through 17 before. It's just two parallel plates. And what we've noticed before is that for some reason they mention here the distance between the two plates, 5 times 10. That's weird that the circle came up, okay. It like tries to predict shapes and sometimes it makes mistakes. So D equals the distance between the plates is 5 times 10 to the -3 meters. And it gives us the voltage of 12 volts. All right. So it asks us to do some stuff like, okay, there's the electric field lines. That part's easy. What's the direction of electrostatic force on the electron? Obviously, the electron is going to go upward because even though the electric field lines point down, electric field lines point in the direction of a force on a positive charge. Since the electron is negative, it goes the opposite way. And that makes sense because just look at the two plates. Okay, the electron is going to go to the positive plate, right? Opposites attract. But I want to talk about number 16 in particular. Number 16 in particular, or also number 17, just talk about that. The electric field is the same everywhere between the plates. It doesn't matter where you are, as long as you're between those plates, it's the same. So calculate the magnitude of the electric field strength, okay? Now, this one's a little bit different. Now, the way we've done this before is we did electric field equals force, electrostatic force over charge. You're given the force. In the question, you're given the charge because it's an electron. How else could you do this question potentially? So if you do it that way, you will get a good answer. But I want to talk about something else. There's this other equation. Electric field equals voltage divided by distance. Okay. Where the heck do we get that equation for? The Regents exam actually uses this in the answer key for this question, though you don't need to use it. But it does not appear in your reference table. Kind of. Let's look at your reference table for a second. So we're going to take two equations, these two. E equals FE over Q, V equals W over Q. I'm going to rearrange both of these equations to isolate Q. If both of those things are equal to Q, can I set them equal to each other? All right, now this next part is going to seem a little bit strange, but bear with me. So what I'm going to do here is I'm going to multiply the left side, top and, well, I'm going to multiply the left side by 1. But what am I going to multiply by? Multiply the top and bottom by D, okay? D over D is 1, so I can do that. So force times distance over electric field times distance equals work over B. Okay? Now I'm getting there. Now, you might realize something. Force times distance is equal to work. So if the numerators are equal, the denominators must be equal. So electric field times distance equals V. E equals V over D. That derivation was a bit much, but that is actually something that you've sort of learned. You've learned those two equations. You've learned that F times D is equal to work. It's just a little bit of math there. But there's an equation, electric field equals voltage over distance, that you could use. So for 16, if you wanted to use that, electric field, it's actually easier to use in my opinion. The voltage is 12 volts. The distance is 5 times 10 to the -3 meters. And let's see what we get for an answer here. 12 divided by 5 times 10 to the -3. We get 2,400 volts per meter, or 2,400 newtons per coulomb. Volts per meter is another way to do the that unit there. I just want to double check that our answer would have been the same if I did E equals F over Q. That would be 3.8 times 10 to the -16 right? That was our force divided by our Q 1.6 times 10 to the negative 19. Yeah, we get basically the same thing. It's off by a small bit, but to two significant digits, it is accurate. All right, so I just wanted to throw that in there so you're familiar with that. That is a way you can solve some of these questions, E equals V over D, but I do not give you that equation on the reference table. So you could either memorize it, you could derive it, but you will never have to use it. There will always be another way to do those questions, right? So don't forget, 7 and 8, make sure you do those on a separate piece of paper or on this piece of paper. Take a picture of your work, upload it to your Google form for today's class. Don't forget we have classes whole week. I will see you some other time, all right? Stay safe.